Hi everyone, welcome back to Math 352. So this is lecture number 3 and it's the second of our online lectures for this course. Okay, so just to recap, the first lecture we had was actually a physical one, which was kind of rudely interrupted by that earthquake there. So that was a lecture on matrix multiplication. The first online video, which hopefully you've had no trouble finding and working through yourselves, was on orthogonality. We were looking at orthogonal vectors and matrices and how you can use those to decompose things a little bit into orthogonal components. And today's lecture is going to be on norms. Okay, so this lecture, along with the last two, and maybe the next one or two, are kind of bouncing around from topic to topic, covering areas that are going to be important for the more complex application stuff that we're going to do a bit later in the course. Okay, so today's lecture is all about norms. Norms basically are how we measure the size of things. Okay, so if you want to know how big a matrix is or how big a vector is by some measure, then the mathematical term we use is a norm. Okay, so we're going to learn all about different ways of using these. We're going to prove some results and just get ourselves a good familiar understanding of how these things work. Okay, so norms, lengths. Probably what you're used to is the standard length of a vector that you've been using in your linear algebra so far, and that is an example of a norm, but as we'll discover soon, there are actually quite a few other ones which are both important and useful as well. So the place to start is norms of vectors. So basically a norm is a function that takes in a vector and gives that vector a real valued length. And mathematically there are three conditions that a function has got to satisfy in order to be a norm. The first one is that the norm of a vector can only be 0 if the vector itself is 0. That sort of makes sense. And otherwise, the length of a vector has to be a positive number. The second one, a little bit more subtle, that the norm of the sum of two vectors has got to be less than or equal to the sum of the norms. That one's much easier to see if we draw a little picture. So if I've got a vector x and a vector y, and I also draw on the vector x plus y, then what rule number 2 actually says is that the green line can't be longer than the sum of the two blue line lengths. Okay, the length of x plus y can't be longer than the sum of the other two sides of the triangle. Okay, if it were, then it wouldn't be a triangle. So that's why it's called the triangle inequality, and that's one of the three conditions, sorry. Final one just says if we scale a vector by alpha, then what we get is the absolute value of alpha times the length of x. Okay, so since we've got these conditions, a good thing to do to start with is to verify that what we've been using so far actually is a norm under these three conditions. So what we're used to so far is the Euclidean length. So we've been writing it like this. To distinguish it from other ones that we're going to come across, we write a little 2 down there, and I'll explain why in a minute. So the 2 norm, or the Euclidean norm, is defined as the square root of the sum of the magnitudes squared, and what we want to do is show that it satisfies the three conditions. Okay, so condition 1 is pretty straightforward. That's the one that says that x has got to be greater than or equal to 0. Well, we're only working with absolute values squaring and square rooting, so that one's obviously true. And won't change the sign. Okay, and the only way that the length of x can be 0 is if all the xi's are 0. So the only way that the length, or the 2 norm of x, can be 0 is if all xi equals 0. Okay, so that makes sense? So that one's pretty straightforward. The next one, however, although being easy to state and easy to visualize, is not quite so easy to prove. So for number 2, I might just switch to a new slide in a second. I'm actually going to cheat slightly, and I'm going to employ an inequality that we haven't actually proved. So let's get a new page after that. Go back to full screen. Okay, so we're going to use a result called the Cauchy-Schwarz inequality. Some of you who are electrical engineers may have heard of this before in your communications courses. And the format is going to look like in our course is like this. It says that the absolute value of the inner product of x and y is less than or equal to the norm of x times the norm of y. Okay, and we're going to make use of that to prove our triangle inequality. So we'll just put a box around you because you're going to be a useful formula. So triangle inequality. So we're going to remember we're trying to prove this: x plus y is less than or equal to norm x plus norm y. Okay, so the norm of x plus y, well actually it's actually easier if we start with the norm of x plus y squared. Okay, so as you know, we can write this as the inner product of x plus y with itself, and then we can expand out the brackets. Okay. You should recognize a couple of those terms. X star x is just the norm of x squared. Plus the norm of y squared. Okay, now the norm of x squared and the norm of y squared, they're looking good because we want that kind of thing in our final answer. It's the x star y and the y star x that we want to see if we can do something about. Now these are both complex numbers, and actually they're the complex conjugate of each other. Okay, so if you imagine this was a complex number z here, then this here is its complex conjugate. Now if we were to draw these on an axis, then you'd have z, and then if you add on its complex conjugate, okay, imaginary part is negative, then you get something that looks a bit like that. Okay, so that sum there is a real number, and what we can see is that its length, by our own mini version of a triangle inequality here, is less than twice the absolute value, or twice the length of this line here. Okay, so the length of this black line is the absolute value of z. So this one's z, this one's z bar. Okay, so what we can say is that sum is less than or equal to twice the absolute value of x star y plus normal y squared. Now we use our Cauchy-Schwarz inequality, which in turn is less than or equal to norm of x squared plus twice norm x norm y plus the norm of y squared. Great. And that is just simply equal to norm x plus norm y all squared. Okay, so finally all we have to do is to take the square root and we're done. So square root, then done. Okay, so that's quite a nice one. We can actually prove the Cauchy-Schwarz inequality later on if you guys want me to, but it's one of these results that comes up quite often, and it's really useful inequality just to have in mind. Okay, and I should probably tighten it up slightly. This is only true for that norm there. Okay, so we've proved number 2. Number 3 was that if we scale x, then we get absolute value of alpha norm x. Okay, now I'm going to leave you guys to do that one as an exercise. Just start with the definition, plug in alpha x instead of x, and it comes out pretty straightforwardly. Okay, so basically what we've managed to do here is verify what we kind of knew to be true all along, that our Euclidean norm is in fact a norm by the definition, and so we can rest easy and we can move on. Okay, now as I've been kind of alluding to, Euclidean norm is not the only one, and it's not always the most useful one either. So what we're going to look at next is the most important types, and in fact the only ones you're likely to ever actually come across, and these are the p-norms. Okay, so they look a bit like the Euclidean norm in their definition, except that instead of having just a 2, they can have any number in our formula here. Okay, so the most important ones are the cases where p equals 1, p equals 2, and p equals infinity. Right, so the 1 norm. Well, basically we stick p equals 1 in, and all we end up getting is the sum of the absolute values of the components of x. Okay, so interestingly, in this norm, all components are weighted equally. Okay, each component is on equal footing. You make a change to any one of the components, then the norm will change by the same amount. Okay, so that's the 1 norm, which is called the taxicab or the Manhattan norm. So actually I'll show you why in a moment. The 2 norm, we just looked at, is the Euclidean one. Now notice with the 2 norm that the bigger elements get squared, and so do the smaller ones, but the effect of squaring a larger element is much greater than the effect of squaring a smaller element. So larger elements have more weighting. Okay, so depending on what you're using your norm for, that can be undesirable. So for example, if your vector x is a vector of measurements of some physical quantity, then what you're basically saying is that any outliers, okay, so unusually large elements, then basically they get weighted much more strongly than they should do, and they can skew results. Okay, so there's one area in which using the Euclidean norm is not necessarily the best idea. Okay, so the 1 norm would be a better option in that kind of scenario. Finally, the infinity norm. Well, I'll let you see if you can work out how to prove that for yourselves. But if you take the limit as p goes to infinity, then what you end up getting is only the largest element has any effect at all. Okay, so it's the extreme case of the 2 norm. Only the biggest one has any effect whatsoever. Has any effect. Okay, so you can see that this might be useful if you're, say, designing an algorithm of some sort where you want to control the size of the largest element in the vector. Okay, so you want elements in the vector to be no worse than a certain value. Then you can easily use the infinity norm to measure the size of that vector. If you get an infinity norm of 10, then you are guaranteed that no other element is going to be bigger than 10. Okay, so let's just take a wee break from the theory for a moment and just see how we can use these in MATLAB. The commands are very simple, so let's just jump across to there. So why don't we just get ourselves a vector. 1, 2, let's just get a random one again. 10 times rand n for 1. Remember that rand n gives me normally distributed random variables. I multiply them by 10 so that they just look a bit bigger. Okay, and just make things fit on the screen a bit better. So what we've got here is we've got a vector, and we're going to work out the different norms. So you can probably see, just by looking at it, what the infinity norm of this vector is going to be. Okay, the biggest element is that third one, negative 22.588. So I'd expect that the infinity norm of x is going to be 22.5885. Okay, the 2 norm, well, it's hard to see exactly what that's going to be, but it's a bit bigger than that, but not a whole lot so. And finally, the 1 norm, Well, that's going to be about 5.3 plus 18.3 plus 22.6 plus 8.6. That's going to be something, I don't know, 50 something. Okay, so 54.9257. So you notice that these norms also appear in the same kind of order. Okay, so the infinity norm, you can see comparing the 1 and the infinity norms, they're always going to be different unless most of the entries are 0. Okay, it's because the infinity norm is only the size of one element, then you add on the size of all the rest of them to get the 1 norm. And the 2 norm always sits in between those two values. Okay, so norms of vectors is very easy to do in MATLAB, and you'll probably be using those quite a lot when you do any programming. Okay, jumping back to our lecture. Actually, before we do that, we'll do a bit more. Okay, so you're used to the idea of unit vectors being vectors of length 1. Okay, so if I were to create some unit vectors, so I'll get myself some angles first, linearly spaced between 0 and 2 pi, and I want 97 of them. Why 97? You'll see. Okay, so here's some theta values. Then the unit vectors that you're used to will be these ones here. So we'll plot cos theta against sine theta. We'll make it blue, and we'll make the lines a bit thicker so they show up nicely on the video. Okay, and finally we'll scale the axis, and then I'm just going to click my run button to run that. I'll save it as lecture 3, that's what we are. And lo and behold, we have a circle of unit vectors. Okay, so these are all the vectors of length 1 in the Euclidean norm. Okay, so any vector here has a distance 1 from the origin. But what if we're not using the 2 norm anymore? What if we're using a different one? So, for example, the infinity norm, that's just the maximum element of a vector. So if I take, for example, a vector 1, 0, okay, so that's that one along here, then that's got infinity norm of 1, because 1 is the biggest element. But if I take the vector 1, 0.8, which is up here, that also has an infinity norm of 1, because 1 is still the largest element. So I'm not going to have a circle of unit vectors, I'm going to have a square. So how can we figure this out? Well, what we're going to do is we're going to set up an array of those points. Okay, so P is just an array of all of the points on that circle, and I'm going to scale each one by the infinity norm. Okay, so watch this. If I say max, take the maximum of the absolute value of P, then what MATLAB cleverly does is it takes the absolute value of every entry, okay, and then it takes the maximum of each column. So that's going to be my infinity norm. So why don't we call that norm P inf is the max of the absolute value of P. Okay? So I've got my vector of norms. Now we want to scale all of our vectors in P to be unit vectors. Okay, so I'm going to take P, and I'll call them P inf. I have to divide each one by that scaling factor, the norm P inf that I just calculated. So P inf, we'll start off by making it P, and then we'll scale the first row and the second row individually. So because I'm dividing by an array, element by element, I need to use dot divide for my division. Likewise, the second row of P is going to be the second row of P, also divided element by element by those things there. Okay, and with a wee bit of luck, every vector in here should have an infinity norm of 1. It looks pretty good. Okay, so we should see a 1 or a negative 1 in every one of those vectors. So if we now plot those points, I'll make them red. Then what I should get is a square. So actually I'll plot it on the same graph as that circle I had before. And there we go. See, so the infinity norm unit vectors in fact are all the vectors on this red square here. So that's pretty interesting. So we should be able to quite easily do the same thing for the 1 norm. So norm P1, instead of being the maximum of the absolute values of P, it's going to be the sum. Okay, so once again, commands like sum and maximum always work down columns of an array. So if I take the absolute value of P, I get a big thing of absolute values. It does every element. If I take the sum of it, it sums up every column for me. So those numbers there are going to be the 1 norm of each of those unit vectors. So I'm going to do the same thing as I did before. I'm going to scale my points P by their 1 norm so that we get unit vectors. I should probably do that right. Okay, once again, so I'm going to divide by the norm, the 1 norm, and then I will plot my vectors, and I'll make those ones green. Okay, so before we do that, why don't we just have a think about what it's going to look like. So for each vector that has a 1 norm length of 1, the sum of the components must be equal to 1. So hopefully, if you think about that for a moment, you'll see that it's also going to be a square, but it's going to be a different one from before. Okay, so here it goes. Any point along here, so 0.2, 0.8 sums to 1, 0.8, 0.2 sums to 1, 1, 0 sums to 1, 0, 1 sums to 1. Okay, so you can see that this is what the unit vectors look like under the 1 norm. Okay, that's kind of interesting. So we've got to get rid of this notion that unit vectors are necessarily a circle, because when we're working with different norms, they're not. Okay, so that was just a little bit of a breather there to get ourselves into that kind of way of thinking. Okay, moving on. So, some more things about P norms? Let's just do a quick example. So if I've got the vector x is equal to -3, 4, then what I'll do is I'll just draw myself a picture of this x. So x1, x2, or x and y, doesn't really matter. Our vector is going to be over here somewhere. There it goes. A highly straight line. Okay, and I'll draw on these little components here as well. So there's a length of 3, it has a length of 4. Okay, so the 1 norm of x is equal to the absolute value of -3 plus the absolute value of 4 is equal to 7. Okay, so the 1 norm of a vector is basically the distance you'd have to travel from the origin to your destination if you can only travel in perpendicular right-angled directions. Okay, so you can see why it's sometimes called the Manhattan or taxicab norm, because it's the distance that a taxi driver would have to drive around city blocks to get from point A to point B. Okay, 2 norm is equal to the square root of -3 squared plus 4 squared, and from high school you know that's going to be 5 without even thinking about it. So that's the 2 norm. As we expected, it's less than the 1 norm, and the infinity norm should be smaller again, and that's just the maximum of absolute value of -3, absolute value of 4, which clearly just equals 4. Okay, so you can see the 1 norm and the infinity norm are slightly easier to calculate because you don't have to square anything and you don't have to take any square roots. All you have to do is just find the maximum or the sum of absolute values. Okay, so moving along. So we've talked probably enough about vector norms for now. What we're going to move on to is matrix norms. Okay, so there's those unit balls that I was talking about before, looking kind of nicer. Okay, so a matrix norm. Well, one way of thinking about matrix norms is a matrix is just an array of numbers. Okay, so if it's an m by n matrix, then it's going to have m times n entries in it. Okay, so those m times n entries, you could consider them just to be a vector of numbers. So actually any vector norm you can think of can also be used as a matrix norm if you just treat it as a big vector of numbers. Okay, so this is a perfectly valid thing to do, and that will satisfy our norm definitions, but it turns out that it's not actually the most helpful way to think about it. Okay, so a better way to think about it is if we think of our matrix A as a transformation. Okay, so if we've got a vector x and we multiply it by the matrix A, we get another vector y. Okay, so our vector x might have a length of, say, 10. Our vector y might have a length of 20. Okay, so in that case, the matrix would have kind of scaled the size of the vector by 2. So one way we can define a norm is to say what is the largest scale factor we can get out of our matrix by choosing an appropriate x. Okay, so what x can we choose that will be scaled the most to get us a y? And that number, that maximum scaling factor, is called an induced matrix norm, and it's a valid norm of the matrix A. Okay, so here's a kind of slightly more technical definition. So given a vector norm, so what the matrix norm is going to depend on what type of vector norm you're using, and a matrix, then the induced matrix norm AP is, there should be a P on there, is defined by the following expression. So the supremum, which is basically the maximum of the length of AX divided by the length of X. So it's saying the maximum scaling factor you can have. If you want a slightly less technical way of writing that, you're basically taking the maximum over X of norm AX over norm X. Okay, another way of saying this is, okay, we can just take the maximum over all unit vectors of norm AX. Okay, so that's actually a kind of possibly an easier way to think of it. Just take any unit. What is the largest vector you can get out by multiplying a unit vector by A? Okay, so that defines the norm of the matrix, and we'll move on and actually have a look at this. Okay, so we've got a matrix A. Let's just move away from that picture again. So A is equal to 1, 2, 0, 2. So let's put that into MATLAB again. There it goes. Okay, it would be a shame to waste our unit vectors that we calculated before, so we'll hang on to those. So you'll notice that if I take A and multiply, let's call it PA equals A times P. So what I'm doing, I'm taking my vector of 2 norm unit vectors, that's the circle, and I'm multiplying each one by my matrix A. Then I get another set of points. Okay, there they go. So I'll put that back in my file. Then if we plot, I'll clear my figure. I'll plot my unit vectors, and I'll also plot my scaled vectors. Once again, I'll make the line a bit thicker so we can see it well on the screen. Then what I get is something that looks like this. Okay, so I just do axis equal. Make sure we get circles properly. Okay, so basically I've taken every vector on my circle, I've multiplied it by my matrix A, which was 1, 2, 0, 2, and this is what I get. Okay, so this is always in fact the case, you always get an ellipse. And the 2 norm of our matrix A, okay, not the vector, the 2 norm of the matrix itself is the distance of the furthest point away on my ellipse to the origin. Okay, so here's the origin, here's my furthest away point, that distance is something like 3. We can work out exactly what it is on here. Okay, you can work out norms of matrices using the same command as the norm of a vector. That distance is about 2.92. Okay, so my 2 norm of my matrix A is equal to 2.92. Now I can do the same thing for my 1 norm. Okay, so I'll call this one PA1. What did I call my points? Can't remember now. P1. Yeah, that's sensible. Okay, A times P1. So I'll call these ones P1. And we'll do this one. Okay, so our 1 norm is that, remember the unit vectors with that square that's rotated around to be a bit like a diamond, and we're looking for the furthest or the largest 1 norm point on this resulting parallelogram. Okay, and think about it for a bit, and it's actually this point up here. Okay, so that the 1 norm of this point is going to be the x value plus the y value. It's going to be 2 plus 2, so it's going to be 4. So my 1 norm of my matrix A is 4. We can check that. Okay, and so you notice it's a different number from the 2 norm, so like the vector norms you get different numbers. We'll just do the same thing one more time. PA_inf equal to A times P_inf. I hope that's what I called it before. If it's not going to work. That's okay. Let's see. Yes, we're lucky. Okay, so the infinity norm, remember the unit vectors with that square. If you scale each vector there by my matrix A by multiplying, then once again you get a parallelogram. This time we're just looking for the point that has the largest infinity norm on the parallelogram. Going around here, so we're just looking for the largest possible magnitude element. So this has a 3 in it, this point here. Nothing else is anything bigger than a 3, so my infinity norm is going to be 3. Once again, we can check that, and it's 3. Now one thing you can see that's different between the vector norm and the matrix norm is the 2 norm is not necessarily sandwiched in between the 1 and the infinity norm. Okay, that property is only true for vectors, not for the induced matrix norm. Okay, so I'll flick back to my presentation. So just what we've done here, I've showed the point that gets transformed to the furthest away point, and basically this is exactly what we just did. So I'll just quickly go through that. Okay, so that's kind of cool. So that is what an induced matrix norm of a matrix is. Okay, now it turns out that the 1 and the infinity norms of a matrix are particularly easy to actually calculate. You don't have to work out how to do it the way I just did then by drawing pictures and things. There's actually a really nice formula for it. Okay, so the 1 norm of a matrix is equal to the maximum column sum of A. Okay, so if A is equal to say it's got 3 columns, then the 1 norm of A is equal to, oopsie, that should be there. That's equal to max of these. Okay, so if let's have a concrete example. If A was equal to this matrix here, 1, 2, 3, -9, 1, 8, 0, 0, 6, then the column sum of the first column would be 10, second column would be 3, okay, so I'm just adding up absolute values, third column would be 11 plus 6, 17, so the 1 norm would equal 17. Okay, so it's a particularly easy norm to calculate. Now, I'm not going to prove this now, but we'll go over this one in our examples, in our first examples class. Okay. Likewise, the infinity norm is just as easy to compute. Okay, so where the one norm is the maximum column sum, the infinity norm is the maximum row sum of A. So if we write A slightly differently, in this case we've got A is equal to A1 adjoint. Okay, remember, whenever I'm using a vector in this class, it's always a column vector. So if I'm trying to write down a row of a matrix, I have to take the adjoint or the transpose of a column to write it down. Okay, so the infinity norm of A is equal to the max, in this case of A1. Again, the one norm, so it's the sum. But now it's over the rows, not the columns. So if I have that same matrix again, 1, 2, 3, negative 9, 1, 8, 0, 0, 6, and I work out these row sums. This one is 6, this one is 9 plus 1 is 10, plus 8 is 18, and 0, 0, and 6 make 6. So the infinity norm of A is the largest of those, which is 18. Okay, so that is a nice way of computing those things. Alright, so to finish off with, that's not the only way to compute a matrix norm. The induced matrix norms are usually the most useful and interesting ones, but like I said earlier, we can actually define a matrix norm as a vector norm, just treating each element as a component of a big n by n times n vector. Okay, so the three rules are the same, exactly the same in fact. Oops, that one's got a bit mucked up. That there should say norm A plus norm B. Okay, so I'm not going to dwell on that, but there is one particular one which is actually quite important and actually quite useful. So I'll briefly give him a mention, and that's the Hilbert-Schmidt or Frobenius norm. I'll usually call it the Frobenius norm. Okay, so there's the definition. Looks a bit messy, but basically the Frobenius norm is just the sum of the squares of all the entries. Okay, so if A equals 1, 2, 3, 4, then the Frobenius norm of A is equal to the square root of 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay, just the square of all the entries and sum the whole lot up. Okay, which equals the square root of, somebody tell me please, oh you're not here so that won't work, 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, square root of 30. Okay, so that's the Frobenius norm. Can also be written as the square root of the trace of A star A. In case you haven't come across that before, the trace of A equals the sum of the diagonal entries, okay, which equals the sum from I equals 1 to M of A, I. Okay, so why is the Frobenius norm equal to the square root of the trace of A star A? Well, I'll just do it for the 2 by 2 case. If A is equal to A1, A2, then A star A equals A1 star A2 star times A1 A2, which is going to be a 4 by 4 thing. A1 star A1, A1 star A2, A2 star A1, and A2 star A2. Cool. Okay, so the trace of that is equal to A1 star A1 plus A2 star A2. Okay, and what have we got there? Well, that's just the sum of the A1 star A1 is just the sum of the squared elements down the first column. A2 star A2 is the sum of squared elements down the second column. Okay, and so the square root of that is going to be the Frobenius norm. Okay, so I've just got one property that's really nice about the Frobenius norm, which is why we actually highlighted it. Okay, so it, together with the 2 norm, they're both invariant under unitary multiplication. What does that mean? If I take a matrix A and I left or right multiply it by an orthogonal or unitary matrix, then the norm or the size of that matrix doesn't change. Now that actually turns out to be a really important property, because in a way it says that you can take a matrix and multiply it by a number of orthogonal ones, and in a sense you're not changing its essential properties like its size. Okay, so this idea is actually one of the key components of a number of the important numerical linear algebra recipes or algorithms of the last century. So we'll be looking at some of this a bit later on, but this is a really important idea. So it's quite easy to prove as well. So what it says, for any A and unitary Q, we have the norm of QA is equal to the norm of A, both in the 2 norm and in the Frobenius norm. Okay, so let's look at the 2 norm first. So 2 norm, well, what is the norm of QA? That's equal to the maximum over x is equal to 1 of the 2 norm of QAX. Okay, now we're now dealing with a vector norm, because QAX is a vector, so this is now the vector norm. Okay, which is equal to the maximum over norm x equals 1 of the norm of QAX. Yes? Okay, so AX is a vector, Q times AX is a vector, we're taking the 2 norm of that. Now remember last lecture we showed that under the 2 norm, which we didn't know what it was called then, that this is true. Okay, so we can basically just say that's just equal to the max over x equals 1 of norm AX, and that is just the definition of the 2 norm of our matrix A. Okay, so that was quite straightforward to prove. We'll look at the Frobenius norm next. Okay, so just to finish the lecture off, under the Frobenius norm, let's see. So we can't use that induced matrix norm definition. So the norm of QAF is equal to. Okay, so I'm going to write my A out in columns again. It's often a very helpful thing to do. We've got n of them. That is equal to. Remember, you can take the Q inside. Okay. Now remember, that is equal to the square root of the individual Q norms of each of those columns. So individual 2 norms squared of each of those columns. Okay, and we know, using that same result again from last lecture, that we can basically make those Q's go away, because multiplying a vector by an orthogonal matrix doesn't affect its length under the 2 norm. Okay, and that is simply the Frobenius norm of A. Okay, well I think that's about all I've got time for today. We'll go into some more detail and a few more examples in our examples class, which will be when I'll next see you. But until then, I hope you have a really good weekend or night or day or whatever it is you're having, and that will be me for now. So I'll see you later. Bye.